This is lecture number 2 on graphical limits. And for this discussion, we're going to be talking about what happens if x is approaching a certain number. This might be like 2. And the function itself seems to be going to infinity. Here's an example. So here's 2. We have a vertical asymptote, and the function seems to be doing this. And you might want to review the lesson on graphing. Vukovic, a typical equation might be y is equal to 1 over x minus 2 squared. Okay, so this is very similar to y is 1 over x squared. That's in your library of functions. You should know that. And in this particular scenario, we've replaced the x with x minus 2, which shifts this 2 units to the right. So the graph shifts 2 units to the right, and sure enough, here we are at x is equal to 2. And my question is, what happens when x approaches 2 to this function? And like our trig functions, I think it's pretty clear that we can say this function, the functional values, increase without bound. They go to infinity. Now, even though this is correct notation, I should note if the function does not approach 1 finite value, then the limit is non-existent. So technically we can say this limit does not exist, and that's also correct. So why do I write equals plus infinity? Well, even though the limit doesn't exist, by saying that the limiting value increases without bound, it sort of gives us a little bit more information on how the limit doesn't exist. It doesn't exist because the function keeps growing larger and larger and larger. If, however, the problem, same function, if the problem was asking, let's do it this way. Let me change the function slightly. Let me get a new picture going. I changed the function slightly by taking away the exponent. So now I'm thinking, here's my parent function, 1 over x. And we know what that looks like. It's in your library of functions. You should be very familiar with that. And again, I'm shifting it 2 units to the right. So 1, 2. Here's 2. And the function now has a vertical asymptote, again at 2, but the function goes that way and comes this way. Okay? And so now the question is, what's the limit when x approaches 2 from the right of this function? What should I call the function? I can just call it y. Y is the function. Here's y. What's the limit as x approaches 2 from the right? And as you come in this way from the right, it's pretty clear the functional values just keep going up and up and up. So we can say equals plus infinity. On the other hand, if I were to ask what happens to this function as x approaches 2 from the left, what should I call the function now? Let me call it this. I'll call it this. This is the function, right? X minus 2. What happens to that as x approaches 2 from the left? So now we're thinking we're coming in this way, and it's pretty clear, I think, that the function's heading down, right? Down towards negative infinity, so we can write negative infinity. Both of those are correct. It would also be correct to say that these limits do not exist. Remember, if the function does not approach a finite value, then the limit doesn't exist. So I could say the limit as x approaches 2 from the right, I don't know, let me call this function u of x, okay, limit of u of x as x approaches 2 from the right is plus infinity. That's correct. I could say the limit as x approaches 2 from the right of this function u of x does not exist. That's also correct. I could say the limit as x approaches 2 from the left of this function u of x is equal to negative infinity, or I could say the limit as x approaches 2 from the left of this function u does not exist. All of these are correct answers. However, suppose I wanted to know not the one-sided limit, but the limit as x approaches 2 of this function, the one I've got graphed here, 1 over x minus 2. Well, I can't say positive infinity because it doesn't behave that way as I come in from the left. And I can't say negative infinity. I have to say does not exist. Okay, and this is the only acceptable answer for that particular question. Okay, so that would be limits. We might want to call these infinite limits. Infinite limits, where you have vertical asymptotes. Okay, the second thing I want to talk about is what happens if we have this type of behavior. Limit as x goes to infinity of some function. And again, we might want to look at 1 over x minus 2 squared, the same function that we looked at originally. Here's 2. We had a vertical asymptote there. And remember, the graph looked like this. Okay, however, now I'm not asking what happens when x gets close to 2. I'm asking what happens when x goes really, really large. So we might want to call these limits at infinity, not infinite limits, although they could be. These are limits at infinity. Probably a better way of thinking about these are end behavior. What is the end behavior of this function? And if we know the sketch, and we know that we have this horizontal asymptote is the x-axis, and the function gets smaller and smaller and smaller as we go out. So we're going to say this limiting behavior is 0. Now that does not mean the function gets to 0. In fact, this function never does get to 0. But this indicates that the function can approach 0, and in fact, it can get as close to 0 as we like. You want to get within 1/1,000,000th of 0, you can do that. Just travel out far enough. And in later courses, we'll talk about how you can actually determine how far out you got to go to make sure that this is within any specified tolerance of 0. I do know the function never gets to 0, but the limiting behavior is 0. Okay, so approaches 0. So we'll call this limits at infinity. One more quick example. Suppose we had this, what's the limit as x goes to negative infinity, and we have a function, how about e to the minus x? Notice that this is one of the functions in your library of functions. Yes, you should be studying those on a regular basis. Y equals e to the minus x. If this is x and this is y, this is your exponential decay, and it looks like this. Okay, so now the question is, what happens to this picture? Again, we're looking at pictures here, as x travels out to the left. Okay, so as x goes this way, further and further out, it's pretty clear that this function is growing and growing and growing and growing, and in fact, it grows very, very quickly. So we can say this limit equals positive infinity. We can say that. So this is a limit at infinity, and it happens to be an infinite limit. We could also say, because the function is not approaching a single finite number, that we are allowed to say, as x approaches negative infinity, sometimes this is read as x decreases without bound. In other words, more and more negative, B-O-U-N-D. This function, and again, I could call it y, I suppose, as long as I know y is the same as e to the minus x. The function y does not have a limit, does not exist. So both of these are correct answers. The function does get huge, it blows up because it does not approach a single finite number. Then we say the limit does not exist. Okay, let me pull up some handout type questions. Here's a question. I think I pulled this off a test from a previous year. And we're considering this function here. And what happens when x approaches 4 from the right, from the left? What happens as x increases without bound? X goes to positive infinity. And lastly, what happens when x gets close to -2? Now, we can work this problem a couple of ways. The first way I want to do it is to draw a sketch. Okay, so I really want to draw a sketch, and we're going to have to go back and remember all the Vukovic stuff that we had way back in October, November. First thing I note is I can cross out that factor, so there's a hole at x is -2. That's pretty clear. And if I sketch the remaining pieces, so now I'm looking at just the stuff that's not canceled out, I see we have a 0 at 3/2. So this is x is equal to 3/2. Note that I got y, or f if you like, 2x minus 3 over x minus 4. In order for this to be 0, I need to make the numerator 0. 2x minus 3 is 0. 2x is 3. X is 3/2. That's where my 0 is. And I also note I have a pole over here at x is equal to 4. That's the number that would make this undefined. So if I said, again, just looking at what was left after I canceled, what makes this thing undefined? Undefined, well, we know it would be undefined if the denominator was 0. So x minus 4 is 0, creates an undefined situation. X is 4, and that's where my pole is. Now, for the end behavior, and again, we covered all this way back when we were graphing rational functions. In behavior, I'm effectively asking what happens as you put in larger and larger values for x. Say we were to put in 1,000,000 for x. Well, this becomes 2,000,000, 2,000,000, take away 3, and 1,000,000 plus, or take away 4. Now, I would hope that you would see that the take away 3 and the take away 4 are becoming relatively insignificant, and it's as though the ratio is 2 to 1. Remember, our technique was if these had the same powers, this is x to the first and x to the first, we looked at the ratio of the leading coefficients, 2 to 1. Okay, and that gave us our end behavior. So we draw a horizontal line here at y is equal to 2. And then we had techniques for drawing the graph. Here's the quick sketch. This graph goes up, and this is an odd pole, so we go like that. Now, and the blue thing really now is the graph of this. Unfortunately, it's not a correct graph completely, because remember we had a hole at -2. In the original picture, remember there was a hole at -2. So we're going to have to go over here to -2 and create a hole in the graph. We still have our horizontal asymptote. There is a hole now in this curve at that location. Okay, so that would be a graph of this original function f. Okie dokie, once we have the picture, we can easily answer these questions. The picture makes it so easy to answer the questions. The first one, number 32. What happens when x approaches 4 from the right? Well, it's pretty clear that the graph is heading up, so we can write plus infinity. What happens when x approaches 4 from the left? That graph is heading down, so that's negative infinity. What happens as x increases without bound? Remember, this is our end behavior. We have that horizontal asymptote at 2. And what happens when x approaches -2? Good question. As x approaches -2, this hole is some value here. It's some value less than 2. Don't know what it is. Here's the easy way to do it. Just take the number -2 and plug it into this expression. Now, you say, well, I can't plug it into here because if I plug -2 into that, remember I get 0 over 0. But I can plug it into this. And so let me do that. I have 2x minus 3 over x minus 4. And I'm plugging in x is -2. So what's that? That's -7 over -6. So I get 7/6 is the answer. 7/6. Okay? Now, all those are good answers. I don't have any problem with that. Let me show you another way of doing this problem, and that will be with our calculator. We're going to do a lot of calculator questions tomorrow, or maybe the next day, but right now I want to just look at the pictures. Okay, so here's my calculator. Let me go ahead and dump in this equation. I have to be careful with my parentheses. Make sure you get everything wrapped correctly. X plus 2, and dividing that by x plus 2 times x minus 4. Okay, I think I have everything there. Here's my graph in the standard window, and it certainly looks like the picture I sketched with Vukovic. And just to make sure I've got everything right, you know, I could sort of hit my trace button. If I put -2 in, that's where the hole's supposed to be. And sure enough, the function is undefined for x is equal to -2. Notice there's no y value there. I could probably, if I hit zoom decimal, you might even actually see the hole. So you would have to look carefully here. But there's one pixel missing at -2. It doesn't create a dot there. In the standard window, it sort of looks like there is a dot, but that's just because the pixels sort of zoom 6. That's because the pixels sort of zip over that x location. Okay, now I don't particularly want to look at the graph. I had looked at the graph by hand. I want to look at the table. So if I do second graph, I come up with a table. Now I want to make sure that the table is useful here. So I need to set it up. I'm going to go to second window, which sets up my table. And in order to make this do what I want it to do, I'm going to go down to the independent variable, which is the x variable, and change it from auto to ask, like that. Okay, I'll leave the dependent variable automatically calculated, and then I'll go back and look at my table. Okay, the table is blank, right? So now let's look at these limit problems. The first one says, I'm approaching x, or x is approaching 4 from the right. So I have to think now. Let me see if I can bring up my calculator. Here we are. Calculator and my smartboard. Okay, so imagine a number line. Here's here's +4, +3, +4, +5. And I'm approaching this particular problem, number 32, says x is getting close to 4 from the right. So I have to think of numbers close to 4 from the right. Well, numbers like 4.1. Okay, so I can put 4.1 in, and the y value is 52. But I really don't want 4.1. I want numbers really close to 4. So how about 4.01? That's even closer. Oh, now we're up at 502. Now remember, graphically, we were going toward infinity, and sure enough, the calculator shows this type of behavior. The closer I get to 4 from the right, the larger these values become. So I can write plus infinity. Okay, let's try coming in towards 4 from the left. Now coming in from the left, I'm talking about numbers a little bit less than 4, like 3.9. So if I put 3.9 in, I get, -48. 3.99, that's even closer to 4. -498, 3.999. Okay, so, and again, the tendency, you see these numbers are getting very, very, very small, negative, so negative infinity. Okay, how about x gets big? This is problem 34. Well, what's a big X? Big X might be, I'll tell you what, let me clear off this. I think I can clear all these out of here just by hitting clear. Clear, nope. Delete maybe, nope. Okay, well, I'll just punch in numbers. I guess it just goes through here. Let's put in a big number like 10. If x is 10, y is 2.8. Suppose x is 100. I'm going up by factors of 10 here. Y is 2.05. Suppose x is 1,000. So now we're way out to the right, and y is 2.005. I'll even go to 10,000. 10,000. Okay, and now it says y is 2.0005. So it's pretty clear, I think, by looking at the calculator, that as x gets large, the function is getting close to 2. And we saw that as the horizontal asymptote. Okay, last question. What happens when x gets close to -2? And again, I'm going to look at a number line to help me out here. So here's -2, here's -1, right? This would be 0. This would be -3, -4, and so forth. And I'm getting close to -2. Now, when I do this, I really have to consider both. I have to consider what happens when x gets close to -2 from the right. So -2 coming in from the right is like this. So like -1.9, -1.9, that's close to -2, or -1.99, that's closer to -2, or even -1.999. Okay, so we have those numbers getting close. If we come in from the right, we were getting those values. Suppose I come in from the left. So now I'm asking myself, what's the limit when x approaches -2 from the left side of this function f? Okay, so what's that? Here was our function f. We're sort of investigating both of these separately. Okay, so now from the left side, it looks like I have numbers like -2.1, or -2.01, or -2.001. Okay, and again, if you look, we seem to be getting close. What happened to my other ones? They seem to go away. I want to get all these in the same window at the same time. Let me go back to table setup just for a minute and make this auto. Look at the table. Okay, I have that. And then table setup and go back to ask. I'm not sure why it didn't clear itself off the first time. Okay, coming in from the right, we had coming in from the right, we had -1.9 and -1.99 and -1.999. That was it. I was doing the same thing twice. Coming in from the left, I've got -2.1, -2.01, -2.001. Okay, and it seems as though these are approaching, the same type of value. It seems to be around 1.166. Let's get even closer. -2.0001. So we're 10,000th away now? Okay, 1.16667, -1.9999. Okay, so yeah, seems to be getting close to about 1.667, somewhere around there. So if I wrote that down, 1.1666, I think I would be good. And in fact, remember we said our answer, when we looked back at the graphical screen, we said it was, 8/7, I believe. No, it was 7. What was it? We canceled these out. We put -2 in, so that was -7 over -6. So it was 7/6. And if we just look and see here, 7/6, and sure enough, 1.6666. Okay, so we could get that by doing the numerical approximation. I don't have any problem with a decimal. If you're accurate to the nearest thousandth, I would be happy. 1.167. Okay. Next problem. Again, let's do it both ways. Let's see how long this is running. Hang on. We're at 24 minutes. Okay. We're going to do the Vukovic picture first, try to do it by hand, no calculator, and then we'll try it on the calculator. By the way, there would be questions, I suspect, that you do not have your calculator available, so you do have to know how to graph these things. Okay, so let's get a picture going first. Are there any zeros on this function? Well, first of all, there's nothing that cancels, so I have no holes. I do have a 0 at 0, and I have a hole at 3/2 again. Or not a hole, I have a point at 3/2, and I have a point at 0. These are the zeros of the function. And now I have a pole at -2. Right, so x is -2. That's the number that makes the denominator 0. Right, so -2. And the numbers that make the numerator 0 are in fact 0, where the origin is. Here's x, and here's g, and the number 3/2. Okay, and behavior. Well, if we were to look at the highest power here, we note that this is a 2x squared, and we look at the one down at the bottom, we note that this is a 1x squared. So again, we're at 2 to 1, which means the end behavior is the same as in the previous problem. This is going to be y is equal to 2. Okay, we'd like to get a sketch going, and we can do that using Vukovic. Note that we have these zeros. Both these are first order zeros. So we're coming in, we're going across and up, going all the way to infinity. This now is an even pole because of the exponent 2. So we're going to come right back down and go like that. Remember, some students were really confused about crossing this horizontal asymptote. The horizontal asymptote refers to the end behavior, nothing about the stuff in the middle. So in fact, there is no problem at all about crossing that horizontal asymptote as many times as you need to. Okay, so there's our picture, and now we can answer these questions pretty easily. X goes to -2 from the right, function goes up. X goes to -2 from the left, function goes up. And x goes to -2, well, both those go up, so we can say up, no problem there. X goes to positive infinity, and g goes to 2. Just to double check and make sure we're not goofing things up. Again, we should be able to put this in pretty quickly. X times 2x minus 3 divided by x plus 2 quantity squared. Okay, so here's our standard window, zoom 6. And sure enough, now it's sort of hard to see the behavior. We claim that this does cross the x-axis twice, and in this picture it doesn't seem to. Let me, if I zoom in, maybe I can get a better sense. Yeah, it does go through the origin and then crosses back again at 3/2. The 0 here, we can verify that. You know how to find zeros, some number between 1 and 2, and sure enough, the 0 is at 1.5, 3/2. Okay, so we have a good Vukovic picture, and we have our limits worked out here. If we wanted to do this numerically, again, go to your table, set it up as ask, right? So ask, and then go to table and put in numbers again. I'd like to clear all that off. Don't want that. Let's see. Okay. I took my function away. Well, you can try it numerically. One more example, and then I'll give you some more problems to do in class. Let's see. Okay, so now here's a function where it says you should know what the graph of this looks like. And this is not a Vukovic problem. This is a log curve. Let's see, y equals the log of x. That's one of our library of functions. Pretty basic curve. You certainly need to know it looks like this. You should know its graph, its domain, its range, a couple of points on it. Remember, this was E1. And this 0 was at 1, 0. Okay, E1 there. Okay, so there's the picture, but this says it's shifted. And sure enough, we've replaced x with x plus 1. So that is now a shift left, right? Left 1 unit. Let's see how I can do this easily. Well, let me just, the 0 is going to go to here. The vertical asymptote, which was x equals 0, is now x equals -1. And the point, which was E1, remember E is about 2.7, is now going to be about 1.71. So here's our picture. This is the shifted log curve. This now is 0, 0, because the 0 was shifted 1 unit left, and this is the point E minus 1 comma 1, because this point was shifted 1 unit left. Okay, there's our picture, and now we can easily answer the questions. As x travels out to the right, this thing grows, gets big, and as x approaches -1 from the right side, this thing goes south. Okay, so -infinity. And again, maybe just checking again with the calculator, not a bad thing to do. This is the natural log of x plus 1. Okay, x plus 1. We'll go to the table, set it up so everything's automatically asked. And we're going to put in numbers. The x is getting big. So 10 or 100 or 1,000, right, or 10,000. And obviously these things are growing. It grows very slowly. The log curve does grow, but it grows very, very slowly. Maybe if we did like 10 raised to the 20th power, I'm not going to put in 20 zeros. Oh, we're all the way up to 46. Yeah, so this thing keeps growing larger and larger and larger. How about 10 raised to the 80th power? Be like 80 zeros. Okay, now we're all the way up to 184. This does keep growing, even though it grows very, very slowly. How about x approaches -1 from the right? And again, think, here's your number line. Here's 0. Here's -1. And we're approaching -1 from the right. So numbers like -0.9 is what we would be putting into our calculator. Okay, so -0.9, -0.99, -0.999. Okay, and these things continue to go down. Down, yes. Enter. Why are we not getting any calculations here? Oh, calculator's acting up. X plus 1. -0.9. There. -0.99. -0.999. -0.9999. Okay, the closer we get to -1, the more these numbers decrease. Okay, so they're getting smaller and smaller and smaller. -0.99999. Okay. Now you do have to be a little careful. It looks like I've actually typed in -1. You see -1 in the calculator here. It rounds off. My more accurate value is down here below. And sure enough, if we actually tried typing in -1, it would say error. We can't do that. Okay, but we can type in numbers very, very close to -1. Okay, so there's another problem. I'm going to stop this video here. Again, you're going to have a worksheet where you can work on problems of this type. Try graphing them using Vukovic first by hand. Then you might want to try looking at your calculator, and you can also try them numerically to see whether you get this consistent answers. And all these will be posted in the next couple of days. Okay.